Okay, so we talked about surface integrals. Okay, we talked about surface integrals last time. And we now want to talk about surface integrals of vector fields. We want to talk about surface integrals of vector fields. Okay. And yeah, a question. Yeah, the remedial problems for exam 4, you have until this Saturday at 6:25 p.m. to finish any that you need to do. And then the work for exam 4 and remedial problems would be due at midnight this Saturday. Okay, so I think there was a chat about that. All right, so orientation of a surface. Orientation of a surface. Okay, so here's a surface in figure 6. Okay, and you have two possible orientations of the surface. So when they talk about orientation, what they're talking about is whether a normal vector, a unit normal vector to the surface, points out from the surface or points inward from the surface. Okay, you can see that based on figure 6 that you have two possible orientations. Okay, two possible orientations. So if we were to look at a surface, if we were to look at a surface here in general, these are two orientations of the surface. Okay. And just like with Green's theorem, okay, Green's theorem, you have two kinds of orientation. You have counterclockwise orientation, which is positive orientation, and then you have negative orientation, which is clockwise orientation. Okay, so Green's theorem. Remember, Green's theorem is the theorem where you determine the work done in that a vector field does in moving a particle once around some closed path. Okay, in a it's a two-dimensional plane, two-dimensional vector field. And the way Green's theorem, section 13.4, is oriented is that it's for positive orientation. However, if you have a particle that moves around a path, not in the counterclockwise direction, but in the clockwise direction, then that orientation would be negative. And in order to compute the work using the Green's theorem, you would just put a negative in front of the double integral. How many recall that from maybe your section 13.4 problems? You had a few problems where you had to worry about that. Does anybody recall that? Maybe not yet. That's not due till Sunday, that homework. But at any rate, so, okay, we want to talk about, we really want to talk about the rate at which fluid flows outward from a surface. So outward orientation is in figure 7, the first figure there, where the normal vectors flow outward from the surface. Okay, and that's called outward orientation. Now the other, of course, is inward orientation. So we have to be comfortable. We have to be comfortable with orientation before we can move forward. Are there any questions? Are there any questions so far? All right. Well, then let's go ahead. let's go ahead and talk about surface integrals of vector fields. Okay, so I'm going to go right to where they talk about it. Okay, surface integrals of vector fields. So suppose that you have an oriented surface with a unit normal vector n, and imagine a fluid with density. Imagine a fluid with density uh, given by that rho value. Rho is a function of x, y, and z, and there's a velocity field flowing through the surface. Okay, so think of the surface as like a net, and there's fluid flowing through the net, flowing through the surface. Okay, the rate of flow per unit area is going to be equal to the density times the velocity. Okay, that's the rate of flow mass per unit time. Okay, and so let me just see here if I can make this help you understand this. Rate of flow the rate of flow mass per unit time per unit area is equal to rho times the velocity vector. So let me just sort of try to make this intuitive for you. Okay. So okay. So we have here rho times velocity vector. Think about units. Think about units. The units for density are mass over volume, right? Hold on here. Now, why isn't this doing what I want it to do? Hold on, class. Okay, I'll have to go back to the mouse here. Let me just see here. So density is defined as mass over volume. Okay. And velocity, the units are in feet per second. Feet per second. So mass per volume, for instance, we can have mass per cubic feet. Okay, mass. So again, we got mass divided. So I'm talking in terms of units. We're looking at this rho times the density, the density times the velocity vector. And I'm trying to justify why the units for that are going to be mass per unit time per unit area. So mass over volume, an example of that could be mass times mass over cubic feet. And then, you got the feet per second here. And so here we're going to have mass per square foot times 1 over seconds. Okay. And this could be written here. This could be written as mass over seconds, okay, divided by feet squared. See that? So I'm doing a unit analysis on this. The density times the velocity field, the units can be thought of as mass per second over feet squared. So this really is a rate at which, for instance, fluid is flowing in or flowing out from the surface divided by the area of the surface. Okay, in other words, it is the rate of flow divided by, hold on, wait a minute. Hold on. Yeah, it's mass per unit time per unit area. That's what this is. Okay, so you really are looking at, you're studying how the rate of fluid flows through this surface relative to the area. Does that make sense? Does that make, like you can have rate, you can have rate, think of it like that. What's the rate of flow per 1 foot squared of area? Okay. So far, is this okay? Is this all right? Are there any questions on this? Okay, makes sense, Christopher. Good. John, and yes, please give me feedback. I really need it today. This is feedback I want. You know, this is feedback I want, right? Okay, so now let's go back to the book. And what they're doing here is they're going to say, well, all right, if we divide this surface S into small patches, okay, we can approximate the mass of fluid per unit time, okay, crossing the patch in the direction of the normal vector. Okay, let me just see here. Right. Mass of fluid per unit time, that's a rate. We can look at the rate that this fluid is flowing through the surface in the direction of the normal vector by this quantity. We're taking the dot product of, hold on here. Hold on, we're going to get it. I don't give up. Okay, so we're taking the dot product of the velocity field given by the density times the velocity vector with the normal vector to the surface, and we're multiplying it by the area of the ijth patch. So in terms of pictures, here in figure 10 is really the scenario. So, you know, we have to have some orientation. If we're gonna study the if we're going to determine the overall rate of flow through a surface of a fluid, and the fluid's dictated by the velocity field, well, we need a frame of reference. So a normal vector perpendicular to the surface on the ijth patch is like coming out of the surface. But of course, the fluid, because of the vector field, it might not be going in that direction. It might be going in the direction of the vector field F. So in terms of this rate, we need to look at the portion of this vector field, the portion of it that goes in the direction of the normal vector. It's like if you have a wagon and you pull the wagon horizontally. What part of the force, you hold the wagon, the handle up, okay, at an angle. Well, the force you're applying, only some of that force applies to the work you're doing, just the horizontal component of the force. Well, same here. The component of the force that gets applied to the flow rate is the part that comes out in the direction of the normal vector. Okay, and if we take the dot product of the normal vector with the rho times the velocity vector, that's just going to give us the component of the vector field that moves in the direction of the normal vector. Okay. Well, Binyam, I got to tell you, I'm not an expert on electric fields. Binyam asks, isn't this, hold on here. Binyam asks, isn't this used also to measure the electric field through a surface? To me, it makes sense, but I mean, some of you have had more expertise in that than I have. I'll just be honest. But Binyam, you say this rings a bell with you. Is that correct? This rings a bell? In other words, this sounds familiar to something you've been doing. Okay, well, in fact, what we are doing is flux. In fact, what we are going to be doing here, we are going to be doing a flux integral. So yes, then the answer is yes to that. All right. So now, very good. So we're just kind of, getting comfortable with things here. Getting comfortable. So, okay, back to this. So now it always helps me to think about what my units are. Okay, what my units are. So I'm going to go back to the whiteboard here, and I'm going to look at this dot product of the vector field with the normal vector and multiply it by the area of the ijth patch. Okay, so let's take a look at that. Okay, so here we got this. We're dot prodding that with the normal vector. Now the units for this are still, right? The units for the velocity field were mass per second divided by square feet. Taking the dot product doesn't change that. Taking the dot product of the velocity field with the normal vector doesn't change the units, right? I mean, right? And if we multiply this by this area of the ijth patch, Well, area is in terms of feet squared. Area is in terms of feet squared in this example. And so what's going to happen is the feet squareds are going to simplify out, and what you're left with is mass per unit time. Mass per unit time. That's what you have. Okay, and that's a rate. That's a rate. Okay, so that's why they are there any questions on this before we go back to the book? Okay, all right. So this is why in the book here they say we can approximate the mass of fluid per unit time crossing the Jth patch of the surface in the direction of the normal vector by, hold on here, by that quantity. Okay? Now, if we were to add up, if we were to look at a bunch of different patches on the surface and add up for each patch every one of those quantities, what would we get? What kind of integral would we get? Well, I mean, we get a Riemann sum if we added up all of these quantities, the dot product of rho v with n times the area of the ijth patch, we'd add up all those areas. In other words, hold on, I'll write it. Let me go back to the board. So, you know, if we have a whole surface and we want to get the net rate of flow of the fluid flowing through the surface, okay, we would, and obviously the vector v, right, is also, that's a vector there. That's a function of, you know, the where you are in the vector field. But if we take the Riemann sum, I goes from 1 to m, and j goes from 1 to n. Okay, this here, you know, as m goes to infinity and as n goes to infinity, what's this double Riemann sum going to become? Okay, a surfaced integral. That's very good. That's right. That's right, Robin. A surface integral just like that. And this here, this surface integral, well, it's a surface integral. It's a surface integral. And it's interpreted as the rate of flow through the surface S. Okay, so far so good. Are there any questions before I go back to the book? I know this material is extremely important. You know, several of our students have already seen it in a class. So I want to make sure we're approaching it from a calculus perspective, but hopefully it's making sense. Okay, so now back to the book. Okay, so then the surface integral of the function, okay, the surface integral, and now our function, right, is this dot product, right? That's our function. That's our integrand. So the surface integral, the surface integral of that function over the surface S is given by this surface integral. And the density and the velocity and the normal vector are functions of where you are in the three-dimensional space. Okay, it is a surface integral. And that's why surface integrals are important. That's why they're very, very, very important. Okay, so far so good. Are there any questions? All right, John, excellent, excellent. Okay, all right. So now that we have this, we can in short notation, if you think about the vector field F as a density times a velocity field, then you can express this surface integral this way. This is called a surface integral of this form. It's see below. Hold on. A surface integral of this form occurs frequently in physics and is called the surface integral or flux integral of the vector field over or across the surface S. Now, of course, we want to be able to compute this surface integral, so we're going to have to, you know, do a few things to make that possible. But let's just continue on. Okay, so here it's a definition, but really it's true. You know, I mean, we showed it. If you have a continuous vector field defined on an oriented surface with a unit normal vector n, the surface integral of the vector field over S is exactly that double integral. And the notation you see on the first integral, they have that dot ds where the S is in bold, like for a vector S. Its notation, it just stands for the flux integral. It just stands for the flux integral. Okay, so whenever you see the double integral on the left, understand it's a flux integral and it means the double integral on the right. Okay. Well, all right, how are we going to compute this? How are we going to compute this flux integral? Well, okay, hold on here. Let me kind of highlight this here. So, of course, the surface S is scratched out in the three-dimensional space by the vector function R of u and v, R of u and v. And the normal vector to a surface, they talk about equation 6, but it's right here in the yellow. The normal vector, so this flux integral, remember, is equal to the double integral of S of the vector field dot product with the normal vector, the unit normal vector, ds, where ds is just, you know, just the regular S for surface area. But any normal vector, if you want to define the if you wanted to find an expression for the normal vector, okay, okay, what do they got here? They got this cross product of these two derivative vectors divided by the length of the cross product. Well, that will get you a unit vector. That will get you a unit vector for sure. Okay, so what they're doing is they're getting in parameterization now with respect to variables u and v. They're getting in the parameterization. So the normal vector can be written as, let me just see here if I can kind of make this make sense for you. One moment. So, you know, you have a surface, and you have a point on the surface, okay, and you have two space curves that intersect the point. Naturally, if we think about, you know, the origin here, we can draw a vector R of u and v that traces out this surface S. Okay, but if we I want to say this the right way. If we hold one of the variables constant, we'll get a space curve. So let me just see one thing here. It's just really notation. I know what I want to do here. One moment, class. Let's see. One moment. Yeah. So this is, for instance, space curve C1. This is space curve C2. But for every space curve, right? I mean, the intersection of those space curves, I can draw two tangent vectors. And I'm emphasizing them here. Two tangent vectors to this point here. And the one vector is the derivative of the parameter vector with respect to u. So you hold the v constant. And the other vector is the derivative of the parameter, the vector of two parameters, u and v, and you hold the u constant. Now, if you take the cross product of these two vectors, okay, I can probably put that. If you take the cross product of those two vectors, you're going to get a normal vector, right? You're going to get a normal vector to the plane that contains those two tangent vectors. And that normal vector there in green is going to be the cross product of your tangent vectors. It's going to be the cross product. And if you want to normalize that that vector, right? If you want to normalize this cross product of RU and RV, you just divide by its magnitude. Okay, and that's how. Well, are there any questions on this? All right. Well, then let's go back in here. That's how then you can replace in the definition, the normal vector can be replaced then by that cross product of the tangent vectors divided by the length of that cross product. And then the ds, you can actually, I want to say this the right way too. Hold on now. Hold on one moment, class. One moment. One moment. I'm just writing something down here. Okay, so the ds, the surface integral, yeah, that makes sense. We've seen this before. If you have a little piece of surface area, you can represent that piece of surface area by the cross product. So think of it like a little patch. Think of it like a little hold on. I want to say it right. Hold on here. Yeah, I think we can drop the IJ here. You know what we're doing. If we want the little piece of surface area, what does it equal for a patch on this surface? We can just take the cross product of the tangent vectors, take their magnitude, and then multiply by a little piece of area. You saw this. You actually saw this back in section 12.6 when you studied surface area. You actually saw that. So therefore, we have our formula. We have it. And Hold on. Now we have it. And so then, the flux integral is equal to the double integral over region D of the dot product of those two vectors, the vector field F and the cross product between the derivatives of the vector of two parameters. All right, and now, so now you know what a flux integral is. Okay, are there any questions on that? All right, Ryan's good with that. Good, good. All right, well then let's look at an example. Let's look at an example here of how we would apply this, okay? So, well, I want to find a good example. I want to find a good example here. And we have one here in example 4. So let me go there. I wanted to do this a little more conversationally. Sometimes when students take notes, they can get kind of tied up in taking the notes, and I just wanted you to have a feel for this. And all right, let's look at this. Hold on here. Flux across a sphere. And I don't know, it seems to like to highlight things. I don't know why, but it's all right. Okay, so find the flux of the vector field across the unit sphere. So this is a vector field, and we know what a sphere looks like. So we can see a picture of this field flowing through the surface. They've drawn a picture right here in figure 11. Okay, so there's the surface, the vector field. Okay, there's the vector field. Does the net rate of change, does the flux, does the rate of flow through the surface appear to be a positive rate of flow or a negative rate of flow? And when I say, and remember, I'm talking in terms of orientation flowing outward. Okay, a positive orientation. Does the rate of flow appear to be like going outward or inward, the net rate? And Ryan says it's positive. Yes, looking at the picture, that and John and Diodath agree. Excellent, excellent. So looking at that picture, definitely the rate of flow, the net rate of flow is outward. Okay, so that means the flux integral should be positive. We should get a positive value for our flux integral. All right. So that being said, well, are there any questions on this? If the rate of flow, if the vector field were, if the vectors were all flowing inward to the surface, would the flux be positive or negative? Flux would be negative. That's right, Ryan. That's right, Diodath. Okay, okay. So let's see how we approach this problem. Okay. So okay. Flux across the sphere. So first of all, we need the parameterization of the sphere. So if we use parameters theta and phi, well, we know in terms of spherical coordinates, x is sine phi cosine theta, y is equal to sine phi sine theta, and z equals cosine phi. Now that's for when you have radius 1. Phi is between 0 and pi, and theta is between 0 and 2 pi. Okay, so, and I know, based on the MATLAB assignments, MATLAB assignment 7, it seems many of you have a pretty good handle on doing integrals, triple integrals. So that's good. That's good. So, okay, well, all right. So what we have to do is we have to write our vector field then in terms of our parameters phi and theta. Well, the vector field, the I component was equal to z, so you have a cosine of phi where the I component is. The j component was equal to y, so you have a sine phi sine theta there, and the k component was equal to x, so you have a sine phi cosine theta there. Okay, so all right, so we're so far. Are there any questions? All right. So what you do is you take the cross product of your, well, you have to find, they mention here, okay, from, hold on, I don't want that, don't do that. So from example 1 in section 12.6, they find the cross product of the two derivative vectors, and then once you know that, you can work out the vector field. Hold on. I mean, really, this is just computation class, and you're going to have to do some practice. But it's just working it out. And now you are ready. Now you are ready. You have the integrand for your surface integral, your flux integral in this case. And so when you okay, so phi goes from 0 to pi, okay, because it's the entire sphere. Theta goes from 0 to 2 pi. And the double integral, well, you have a double integral of a sum. That's the sum of the double integrals. And then they realize that you can split up those double integrals. The integral from 0 to 2 pi of cosine theta d theta equals 0. Okay, because if you look at the graph of a cosine function, you'll have positive and negative area that all cancel out from 0 to 2 pi. And now you have what's left there. And so, that being said, I'll show you the entire portion. Obviously, they left out steps, right? They left out steps here. Okay, they're just trying to save time. But of course, on the final exam, I would want to see your work, see those steps, so that I can see you understand the concepts. But they end up getting 4 pi over 3. That's what they end up getting, 4 times pi over 3. And so the rate of flow is positive, and that's the rate. Are there any questions on that? All right, then let us continue here. Let us continue a little further. Okay. So, well, they say, actually, let's interpret this result. If, for instance, the vector field in this example 4 that we just talked about is a velocity field describing the flow of fluid with density 1, okay, then 4 pi over 3 represents the rate of flow through the unit sphere in units of mass per unit time. Okay, that's the flux. Now, of course, because we had a sphere, we had to get the parameterization of the sphere to do this problem. But again, in the case of a surface, okay, in the case of a surface where the first surface can be written as z equals g of xy, we can think of x and y as parameters, and then, you know, the cross product of those derivative vectors actually equals what you see there. The negative partial of g with respect to x times I minus the partial of g of y times j plus the k vector. That should be a k vector. And so in that case, the formula collapses into this formula here. So generally, I like to I don't like to use these formulas where, you know, z is a function of x and y. I just personally, I like to always use the key formula that works all the time. The key formula that works all the time is this formula. It just, for me, makes my life easier if I only have to worry about one formula, right? So, are there any questions on that? All right, let me stop there. Let me stop there on the recording.